sorry for giving you all a slightly awkward schedule, but I say I've not quite given this in a 2R format before, and I wasn't sure where the break was going to land, but exactly in the middle of this is not where I wanted the break to land. So this is just an example now walking through. I've described what the allocator traits do for you. That's the main change we had for C++11. So I'm going to give you an idea of what's under the covers there, because I always find it's easier when I'm dealing with a system if I understand how it's implemented. I don't need to know the fine guts of the implementation, but just understanding some of that gives me a lot more confidence in using it. So we're going to walk through ours describing a lot of the C below parts of the standard contract. This is the guts of how this stuff is implemented. It might give you an idea of the cost of what your compiler is doing as you're using some of this as well. But the idea here is right at the bottom of the slide, I'm trying to figure out for my allocator what size type is. By default, size type is determined to be the size type if the allocator has a size type, or we're going to find some magic incantation to find a good default for size type if your allocator hasn't given me that type def. And this is what we're about to jump into. But it relies an awful lot on this language feature. So if I really want to see a show of hands at this point, who feels they're familiar with the notion of SFINAE in C++? Okay, I'm seeing a good broad set of hands, probably just 2/3, 3/4 of the room. But so the remaining quarter don't get completely left behind. Bear with me. I hope I don't go through this too quickly so that people keep up with me, or not too slowly for the people who are familiar with the material. SFINAE is an interesting part of the C++ template system that was not provided for the purpose we're about to put it to. But it's an important property when you're trying to deal with templates on a large-scale system. For example, take a look at this makeChild function on the screen. It's going to return t::type, where type is a nested type within whatever the pointer you give me happens to be. So it makes sense whether this will compile or not, as I call it, depending upon whether or not type t has a nested type. But if I have additional overloads of the makeChild function that are going to be a better match than this, because I'm constructing makeChild for a very specific thing that doesn't have the nested type, the existence of this overload would force my program to fail to compile, and that would not be a good thing. So the rule that went into C++98 was, if t::type doesn't exist, I just can't deduce t, so this function drops out of the overload set rather than being a hard error. So this is how we can overload functions that have interesting properties based upon your template, and your programs can still continue to compile. It was a simple convenience to make sure the language didn't fall apart. But it discovered that this convenience could be turned to other purposes. This turns out to be the basis we can do an awful lot of compile time introspection by arranging special cases whether or not that overload will fail or not to be deduced. And we actually provide a facility in the C++11 library called enableIf that automates an awful lot of setting up this SFINAE condition to succeed or fail just upon a simple Boolean true or false. So here's an example of how SFINAE might be used for compile time reflection in practice. I'm trying to figure out whether or not my type has a nested type def called pointer. So I'm going to create two structs called trueType and falseType that have distinctly different sizes. I'm creating an overload function because, as we said, SFINAE is built around the notion of overloads, called sniffPointer, because it's sniffing out whether or not my type has a pointer or not. And then we'll return trueType and falseType respectively. One will take a parameter, type name t::pointer star, because if I have a pointer type, that will match, and that will therefore be the overload that's selected. And just to make sure anything can be called here, I'm passing pointers, and I can always pass a pointer to anything. It will go to a C-style ellipsis. The benefit of the C-style ellipsis is in the function overloading rules, especially when we have partial ordering for templates, it's always the worst possible match. So if any of the other overloads in this set succeed to match, there will always be a better choice than this. It will never be ambiguous. So now, by using size of, so a feature from the language, I can say what would be the size of if I called this function. I never actually need to implement the functions. They're never going to be called. But I do need to ask the comparator to do the overload resolution and figure out which of these two types would be returned. In C++03, I can't do much with those types, but I can find their size even without trying to instantiate and create objects of this type. And that gives me something I can query at compile time. So I can now create the hasPointer type trait. This is simply static const bool to say static const bool is my result. It's true if the size of the returned value is the size of true type, otherwise it's false. So I have now written a reasonably simple type trait to detect whether or not my class has a pointer nested type def, which, as you saw, was one of the properties we need for implementing the allocator traits. First of all, I need to see if I have this type def, then my result will be that type def. So I can now try and implement something like this using hasPointer. My allocator traits for the pointer type def might be something like this. Type def, type name conditional is another C++11 standard type trait that says if the condition I pass in the first part evaluates to true, I get the first type. Otherwise, I get the second type. So again, it's compile time if type switch to pick the appropriate type out. So if the type trait returns true, I will get type name alloc_pointer. And if the type trait is false, I will deduce to the allocator's value type. Remember, I said it's not optional that the allocator has a value type. That's a mandatory part of the system. So I know I'm going to find that. So the allocator type becomes the pointer, which is great, apart from the fact I was trying to work around the fact I don't have this type, so I still can't use it here. So it doesn't quite go like this. We still need a bit more indirection. So we end up perhaps with something that looks a bit more like this, where I have a different sniffing technique here, where I'm going to pass a second parameter to my trait, which will say what the default pointer should be. So I'm going to use my sniff trait to figure out what I'm passing in the second position. And my sniff trait will then say, if the result type is true, I can be alloc_pointer, because I know that's true. But by default, I get where it's false, or false is the only other value the bool can be. The primary template says, I go back to being the pointer that you saw before. And this actually means I no longer need to use conditional. This is done both steps in one, so my type trait just becomes default pointer is a result of invoking the default pointer type trait. So I've got my one level of indirection now going through this type trait. Yay! And that's pointer. Before we look at size type, we've got some interesting new features were added to the C++11 language. Decal type was a big one, because this actually lets us directly get what is the type of that expression. That can be very handy, especially as we're manipulating lots of parts of the type vocabulary here. Late specified return types on functions allows us to deduce types of expressions based upon arguments we might be putting in, so we can have much more interesting function results coming out in order to start using combined with decal type to say, get my result from what would be the result of that kind of a function evaluation. The rules for SFINAE were greatly generalized. In C++98 and 03, there's a small bullet list of it. Under these conditions, we have the substitution failures are not errors. Otherwise, all bets are off. You're going to get a hard error. If you start looking at private members or all sorts of different, just valid parts of the language, they don't fall under the SFINAE constraints. For C++11, we just generalized that set and said, if I can't form that type expression for any reason, that is now a SFINAE constraint. So that simplifies a lot of the things I might have to worry about in this area. And again, alias templates do make life a lot simpler when you start dealing with a lot of template metaprogramming kinds of issues. So, coming back to my original question, what happens if I'm trying to figure out the size type? Well, in this case, I'm no longer going to create an additional type trait. Turns out this bites us an awful lot at Bloomberg, that type traits are classes. Classes have associated type ID and type info. And simply creating a class, if you create enough of them, and we have very large software that has a lot of different types of objects, simply creating a lot of types is expensive just on the compile time size of your system. So if we can produce these type traits just with functions I never define, there's no additional type information coming from these. So there's actually a little bit less information, overhead on the system object files you're generating as a result. So this is kind of a nice little tweak that we're switching to. So we're going to do the same kind of idea, though. We're going to have an overload based upon an ellipsis to be what we drop back to by default, and passing an int in this case as my just disambiguator. And we're going to have a couple of expressions. So whichever one of these expressions matches the type of that expression is exactly what I want. So by default, if I've got the size type, that drops straight out. Otherwise, the rule says I have the unsigned type corresponding to whatever the difference type of my allocator is, which now is in the result of my type ID, so it automatically forwards to let's go off and figure out what difference type is. Well, again, moving to C++14, we added alias templates to an awful lot of the type traits in the language. It just simplifies this. One of the things you'll notice is this horrible, nasty use of the type name keyword because the type is dependent upon the parameters of the template. That just drops out, so the syntax is actually nicer and easier to use. So these alias traits are probably the way to go if you have a C++14 compiler and you're trying to play with similar kind of tricks and techniques. So, figuring out difference type. It's a similar kind of dispatch because by default, if you have a difference type, we get that from calling with a 0, and it ends up with the allocator's difference type. Otherwise, you've not given me a difference type either. So what difference type should I use? So I'm going to jump 2 slides and then back one. I got these slightly out of order, potentially. Turns out that the difference type, as you can see in red, is going to depend upon my pointer type because it's the difference between 2 pointers. And how do I find the difference between 2 pointers where the pointer could be an arbitrary fancy pointer supplied by the user? Well, we need another traits type. So C++11 also has pointer traits that define a couple of very simple properties about pointers. They give you an element type, they give you the difference type between 2 pointers, and they do the rebind. So if I've got a pointer to int, I can create a pointer to double by going through the rebind. And each of these times you see a C below, that means that your library vendor's doing this kind of crazy template metaprogramming I'm showing you at the moment to figure out some formula to get those answers. And finally, we have the other thing you can do with a pointer is I can get a pointer to something. R is going to be a reference to something, but if the type that I've instantiated my pointer with happens to be void, I'm not going to get a reference back. So there's just a little bit of finessing around the ideas of void stars. So, end result of our difference type is we come back to this slide. We're up at the top now where we're going to go to the pointer traits and say, the pointer type of my allocator, give me the difference type of that pointer type. So of course, we saw here's how I would express, with the modern notion I'm suggesting for type traits, how to get the pointer type out, which we saw a few slides back. Same idiom. Finally, we've got one chain terminating. Is value type, or it is the pointer type that was embedded? Yes, we have one result. But that was just so we could feed back into this trait that says I want the difference from the pointer traits now. So pointer traits difference type is the difference type of the pointer, or ultimately, if the pointer doesn't have a difference type, it's putative t, and putative t in turn is the difference between the decal type I get from 2 pointers. So that finally gives me my answer for the difference type of my pointer to pass to make signed to become my size type of my allocator if the allocator type doesn't happen to just supply the type def for me anyway. So, and final picture, we're done. Question?
One naive question. I see that you are coded 0 in the
Yes.
third. So wouldn't you always resolve to the second point at difference type?
Okay, so this is the key issue about the SFINAE. The 0 says I'm going to try and match the overload that matches an int, but I can match that only if the type has the nested type def. And otherwise, it's going to go to the ellipsis. Everyone in the room with me so far? I'm happy to take questions at this point.
So, we get the point difference type. You have type name allocator, but I don't see allocator as a template parameter.
It's because there's a bug on the slide. Thank you. Yes, that should be pointer.
I often use the trailing return types, but I don't see the reason why you're using them there, since we don't see the names appearing in the beginning of the function.
Sorry, could you repeat the question for me?
Why are you using the trailing return types for the functions in this case? I don't see really why.
My reason for going for the trailing return types is it just ripples all the way up. I always use, as you say, I just like the trailing return type syntax. It's just consistency. So yeah. The question was, why am I using trailing return types? Because not all of these cases have arguments where I need to put a trailing return type. I could have put the same expression at the front of the function name. But yeah, I find auto function name helps me find the function name very easily. It lines up when I'm trying to see how these traits are dispatching, and having the arrow result type is the result in the type system. It's actually a meaningful place for me to find it. Purely a matter of convention and style in this case, though.
In terms of templates, you can call it a specialization, but here you're looking at the late return type. Is it also called specialization? Or what is it called?
Okay, the question is something, do we have some confusion with the terms specialization and late return type? So what we're using is, when we say late return type, C++11 has this syntax where we can use auto to declare the function name, and then we use the arrow to provide the return type. That, in any form, is called a late specified return type. Specialization is which template is being called. How do I specialize that template? So they're just completely different things, which is possibly why I'm not understanding your question.
So it's not called specialized when you're referring to a late return type, right?
Sorry?
So it's not called specialization when you're referring to different late return types.
Yeah, the specialization has nothing to do with the return type. The specialization is which template was called, and that is the specialization that was chosen from the overload set.
I believe the question is, do you call what you're doing here with your two pointer difference types? Are those two overloads or two specializations?
Okay, so the question is, when I'm pointing to this thing on the screen and I've got two functions there, and I'm talking about picking the specialization from, am I talking about specializations or overloads? So we've got an overload set of two declared functions and function templates here. One specialization from that overload set. Because they're both templates, they actually represent more than one function each. So a specific specialization from among those overloads is going to be selected. But the specialization is the name of the actual final function that is chosen, and the template parameters are then supplied. So, second slide is where things get, it could do most of what you saw on the previous slide with C++03, but as you saw from the original way I was trying to formulate the templates with class templates, it kind of got ugly. This problem I found much harder, if not impossible, in C++03, which is how I'd implement the construct call for allocator traits. Now, the formula for construct is, if I can call construct on the allocator that you gave me, with the parameters being supplied to that construct call, then I will invoke construct on your allocator. If I can't find that call that will match, then I will just do an in-place new, forwarding those arguments on again. And trying to check, can I call this function with these arguments? In C++98 and 03, I'm not sure I've ever figured out an answer to that question. And this turned out to be something that was much easier to solve with a similar kind of idiom in C++11. So again, this is mostly a diversion for those who are looking for interesting template metaprogramming techniques. I found the idea of switching everything out to trying to do decal types and late specified returns types helps a lot. So in this case, the function I'm calling is void, and will have a void return type regardless. So I achieve that by actually casting the expression to void to say, does this expression compile, and then cast it to void. So that is sufficient to create the SFINAE condition on will this construct thing work, which largely is a consequence of, A, I've got a late specified return type so I can use the arguments that weren't available to me in C++03, and I also have generalized SFINAE, so that for any reason that causes compilation to fail, I know I'm going to get a SFINAE condition. So I have no idea how I would have done this in 98, And this turned out actually to be fairly easy in 11 once I addressed the problem. The reason I get this to be a SFINAE and not ambiguous, you'll notice I can't use a trailing ellipsis here because I'm passing a parameter pack that's going to swallow all my arguments. So the way we got around that was the pointer I pass is if it deduces to be target type, because the SFINAE can fail for any reason, doesn't need to be because of target type, I get the first template. Otherwise, a void star will match everything and be a weaker match. So this is how I got to create the disambiguation and keep the SFINAE checks going here. So these are the kind of techniques that your library vendors are using to implement allocator traits that make it very easy for you to write allocators and let all this deduce. And this is what's happening when you let them deduce if you don't supply those methods. So a bit of seeing the wizard behind the scenes. Anybody got any more questions before I move on? Okay. That's just about the end of allocator traits. A couple of points to think about when you're designing your own allocators, though. As I said, we have this notion that you can return what I'm calling fancy pointers if you don't want to return a raw pointer from your allocator. They don't tend to work with what people think of as smart pointers, though, where the pointer itself owns the memory, because the allocator is managing the memory. And if the pointer and the allocator both think they're managing the same resource, they start to get into some kind of conflict. And you might be able to make this work, but the act of trying to do this, saying, oh, the allocator and the pointer know about each other and there's some kind of dance happening behind, it tends to make life much more complicated, and you're generally better not going down that design in the first place. So my experience is you don't want to return smart pointers. What you're returning is iterators, because I've got to be able to walk the range from the fancy pointer that you return me that's translating for some other address space or doing some other interesting thing that doesn't connote ownership. And the other important point is stateful allocators need to share that state. Because when I make a copy of an allocator, it's required that that copy compares equal with the first one, and they can interoperate on the memory they allocate. That's why my earlier example, the buffer was on the stack and not actually a member of the allocator. Because when I make a copy of the allocator, I've then got a different buffer, and those two allocators cannot interoperate with each other's memory. So you do not want to be allocating internal memory out of your allocator itself. You want some kind of shared resource that the allocators are all in turn using. So general points on the allocator space before you start designing and working on your given allocator. With that, I'm going to take a quick look like now we have allocator traits. What is it like to implement an allocator? So this is standard allocator in C++98. Switch over to me being fancy. I like my new C++11 type syntax. That print is small. Don't worry about it. The gray stuff drops out because that can be deduced for us by default now with the allocator traits. The yellow stuff was just never used at all. So we end up with something that looks much simpler like this, which is hopefully comes down to a more readable size. Even looking at this, the destructor and the copy constructor can be defaulted, especially for this kind of allocator that's stateless. Even the default constructor might default but by simply not declaring it. The trouble there, of course, is we do have to create this constructor that says I can create any other allocator, rebound for a different type to the same type. So as soon as I have any allocator, any constructor declared, the default will not implicitly generate for me, but I can explicitly request it with equals default if I want it. So something like standard allocator could really become much simpler. But we don't do this because this went out in C++98 where people were calling all those member functions directly. So for compatibility, the C++ standard allocator still has the old interface it always had. But in the simplified world, it could now be this simple. This is deemed to be our platonic ideal of where an allocator can get down to. And as a second example, coming back to our notion of where Bloomberg were coming at from this, thinking vocabulary types, we want to be able to provide an allocator where the type's picked at runtime rather than compile time. Vocabulary types being our big motivation. What we ended up with is a class we call Allocator, is our base class. It's got two key methods, allocate and deallocate, that are pure virtual functions. This is basically a copy-paste from production code because I wanted to give a real example and then just cleaned up with some comments and things dropped out. But essentially, this is what our allocator looks like in BSLMA as part of our open source distribution. This isn't an allocator, but this is what our allocator is going to use. But this is actually our vocabulary type for allocators in the system. What we end up with is, this is what our allocator looks like today in C++98. We still support a C++98 implementation. If you look at this carefully, you can see on the next slide, unfortunately. This is everything that goes away with C++11. What I was trying, jump on a few slides. No. The blue stuff is what we're adding, but it's not so obvious back here. Basically, we're storing the allocator pointer internally, and we're implicitly convertible from that allocator pointer type so that a pointer to our base class actually looks to a system using our allocators as if it were a real allocator, because it will construct one of these through implicit conversion. So looking forward to the day we can port our stuff properly to C++11, all the yellow and orange stuff goes away. What was the red one? I can't even read that on my screen here. The copy constructor. For some reason, I've turned the copy. I can't even remember what I was thinking of when I wrote that slide. For some reason, the copy constructor turned orange. I guess we can just take the implicitly declared copy constructor will do the job for us, so we don't need to write it, but we do need it to be available. Again, everything's getting really tiny. Those are the changes we've made. So these parameters are going away, and then we get the C++11 interface that hopefully is now a bit more readable. I've just shown you how we got here. So internally, we're keeping a pointer to the allocator you're going to pass to the constructor. D_mechanism is a very Bloomberg kind of convention for naming these things. That blue's a little bit awkward to read, unfortunately. We've got this implicit constructor that takes a pointer to our polymorphic class, and then we've got an additional method at the end that says, called mechanism, that says I can now actually get that allocator back. So once I'm using an allocator, I always have the ability to query which allocator are you using. And of course, we have the new C++11 thing that says select and contain a copy construct that should actually be taking an argument for another allocator. That's another typo on the slide, sorry. So we should have another argument here that's an allocator by const reference, but we're going to ignore it and return what in Bloomberg will be a default allocator. So there's the interface. This is what an implementation might look like. Allocators can be very simple to implement. All we're doing is we're passing the allocator supplied to us down to the appropriate member, and then delegating the method, again, in turn, to each of those members. For the destroy function, I just invoke the object's destructor. And for the construct method, I'm calling the in-place construction here. Actually, we do something that's a little bit more interesting there, and we're going to come back to that after another example. Question at the back.
Alisdair, in this example, is your nested type pointer a T star because it was not defined above?
Correct.
It's a T star?
Yes.
Okay, thank you.
That's it. Thank you. It's exactly the point we were making on those previous slides, so sounds like it worked.
How is this related to what standard? This is the Bloomberg app.
This is our Bloomberg model. This
How
is
does this relate to what's
this is the inspiration of what's going into the fundamentals TS, where we've, as part of the standardization model, it's been cleaned up. The allocate actually takes an alignment as well as asides, but I wanted to give something from working code that I could point to. So, but yeah, this is an illustration motivation that now we have the allocated traits, we can do this kind of thing, coming through the fundamentals TS as an application that way.
How can it manage to find out the alignment?
Yes, this is our current code today we use at Bloomberg. We just always assume maximal alignment. The one that we propose for standardization, the allocate call additionally takes an alignment parameter, which there and then there.
Just to clarify on the previous question, so the C++11 containers can work with C++11 allocator traits, so that if I wrote this code today myself, it would just work.
So the
This implementation is coming in the TS.
Yeah. So the question is, or essentially the question answered itself. I'll repeat. C++11 supplies the allocator traits, and all the containers in C++11 are now implemented in terms of those allocator traits. So if you wrote the code on the slide today and plugged it into a C++11 implementation, it would just work. And what's coming in the fundamentals TS is an enhanced version of this based upon standard review that adds support for things like alignment in addition to what we were directly addressing here. So this is in the standards process, but in a slightly different form.
So
Question? Sorry. Question?
the BSLMA allocator uses a virtual function to allocate and destroy, right?
Yes.
So in terms of like type erasure, that problem's already solved. If you have a string class that has a pointer to this, you can treat strings with different allocators, you know, as just a string.
Yeah,
So why is this class again needed to wrap it again? Is it just like a value type kind of wrap?
So the question is, we can do an awful lot with what we're seeing here with type erasure techniques, where the allocator is no longer, again, not visible as part of the type system. So what is our benefit from making exposing the mechanism as a virtual interface rather than just always implicitly doing type erasure? And it turns out, as you start combining systems and trying to pass allocators from A to B to C, you often do need to actually get back at the underlying allocator and query the allocator properties of that allocator to allocate for a different type of object. If I've type erased the allocator, I no longer have the ability to recreate an allocator, do the rebind effectively to create allocations for a different kind of object.
What do we gain by wrapping the allocator again in another classical allocator?
What we're gaining is the allocator interface as a virtual function that manages allocation, and I can go to that interface for any allocator that I can get the type erased whatever that allocator was and still query it. Whereas if I've just got a type erased allocator, I can't get back a handle and know how to call its allocate behavior. So if I want to pass the allocator from one container to another container and then do additional allocation, I need to somehow get back that type erased allocator in a form that I can use it in a completely different context to do another allocation. I need to reconstitute the type that was erased. By using traditional virtual methods, I don't need to reconstitute the type that was erased because I've got the virtual pointer to just the methods I need for the allocation behavior.
Is this just like a non-virtual interface?
That's how we implement it for the fundamentals TS, yes. But sorry, the question was, is this like a non-public virtual interface?
This probably default underscore allocator is just the default VSLA.
Yeah. So question is, the default constructor calls this function default underscore allocator, and yes, the idea is if you don't supply an allocator, our default is going to do something useful. It will go to a general default allocator we have for the system. The reason we call this through a function is we actually have the ability to change the default allocator used by the system, which you would typically do in main. It's a shared resource. You don't want the whole system everywhere changing it at random, but the ability to install a different default, especially test drivers, we always install a test allocator that's going to track for memory leaks, is an important property for us. So, but this is just, the idea is to show it's reasonably easy to implement an allocator that's going to do something fairly interesting. I hope that's an interesting example in that area. Question at the front.
So, your mechanism allocator there, does it have to be able to allocate raw bytes worth of things, or can I make it a type specific?
So the question is, my mechanism allocator here, does this just allocate raw memory, or can I make it allocate specific objects? And that's the other reason we've gone through this type wrapping. If I want to have a generic vocabulary for allocators that I can use throughout my whole system and supply at runtime, those can't have different types because the allocate method would not be overriding the virtual method correctly. So the BSLMA allocator protocol we use, the virtual interface, traffics purely in raw memory. But the BSL allocator that wraps it is a C++11 allocator that traffics in objects, so that then does the translation at that part of the interface.
But if I wanted to have a mechanism that did not deal with raw memory, then we're worried about fragmentation into the pool, for instance.
So if you wanted a mechanism that doesn't traffic in raw memory, you could create your own protocol similar to how we created ours to satisfy your own needs. what we wanted for vocabulary purposes, we did not want type intruding upon the kind of allocator being used. So it was important that was a complete type erasure in this sense. So just an interface of raw pointers was what solved our problems.
So in that case, what would I do with the template class view, allocator, constructor,
Well,
kind of thing?
I don't know the motivations for your case. You would think about what works in your case and say, yeah, what do I do for a default constructor? What happens in these cases? In our case, it was just reasonably simple drop-in one-line functions, apart from the construct call, which I will get back to. So what's it like to implement a container using the C++11 model? This is the other important piece of material we need to look at. So I'm going to propose a simple type here called dynarray that is totally nothing to do with the dynarray that was proposed for C++14, but happens to solve a similar purpose. My idea in my head, thinking of this example, is dynarray is going to, at construction, it's going to dynamically allocate an array, kind of like a vector, but then it's never going to reallocate it. It's just a dynamic array allocated once. And I'm going to walk through, as you can see, I've got, do I have it? Yeah, constructor on the screen shows that I can construct it from a C++11 initializer list. That will walk through our example of how we're going to implement this. So the interface, this is a classic C++11 interface now. We're not doing that runtime allocator. So templatized on the element type I'm storing in the container, templatized on the allocator, and the allocator defaults to standard allocator of T, so that if you say nothing, you get the same default that everything comes out of C++ tends to drop down to. Implementing it, we look at the private parts. First thing we're going to do is we're going to create an alias for the allocator traits, because we'll be using the allocator traits an awful lot through the various methods of this class. So I get the allocator traits of the allocator you supplied me. I also need to know the pointer type, because I'm going to store the pointer that I allocate. And that might not be T star. So now I've got my alias to the allocator traits. My pointer is whatever the allocator trait says the pointer is. So my two data members are going to be the pointer of the data of this pointer type and a copy of the allocator. And I guess it's arguable in this case whether I need the allocator, because I can allocate only at construction and then I'm done, but it makes our example much easier to keep the allocator around. So now we're going to implement that constructor. So first thing I'm going to do is I'm going to default initialize my pointer, so I've at least got some variety of null pointer that silences an awful lot of compiler warnings that get annoyed about these things if you've got uninitialized data members. And I'm going to make a copy of my allocator. So now to initialize my memory, I'm going to want to go off and allocate some memory using the allocator. So I go to the allocator traits, and I call allocate, passing it the allocator, d_alloc, and say, how many elements am I creating? Is the number of elements that were in the initializer list that the user supplied me when they constructed me. Then I want to have that as a native pointer so that I can actually call my construct methods. This question came up earlier. Well, I've allocated memory for these many things. I've got essentially, hopefully, uninitialized memory there. But I can take the address of whatever that first element is and turn that into my raw pointer. Address of is a standard library function in C++11 that says, if I've got a really awkward, annoying user who's written their own type T that overloads the unary addressive operator, something like a Microsoft COM pointer, or they could just make it return void, make it private. They can do whatever craziness they want. We still get the address of that object. And again, magic. So that's what the address of. And again, I'm using C++11 auto just to make my life simpler here. You'll mixed opinions as to where auto is appropriate. There's some very enthusiastic auto everywhere. There's some use it only when absolutely necessary ideas. In templates, auto is a lifesaver so often. So you'll see auto on quite a few of these slides going forward. OK, I've allocated my memory. And so now I want to go off and initialize the elements. So I'm going to iterate through with a for loop over my initializer list, which C++11 makes really simple now. So take a reference to each of the elements walking through in turn. I now call allocator traits construct to initialize that element. I pass it the allocator, and I pass it the address that I've now got for my element, and the element I'm making a copy of, which is going to call the appropriate constructor, then increment my pointer so we can advance to allocate the next element in turn. If, in the middle of construction, halfway through my sequence, a copy constructor throws, I now need to make sure I at least go back and unwind and destroy all the other elements. So I now go through the for loop again, again starting with the address of the first element, call allocator traits destroy, pass it the allocator, pass it the address of the element I want to destroy, and I now can, having destroyed all the elements, I can restore to the allocator all the memory it allocated by, again, allocator traits to call the alloc, pass it the allocator, pass it the address, or the pointer that it gave me, or whatever kind of smart pointer that might be, and tell it how many elements it gave me, and then rethrow the exception. I don't need to worry about catching after the first allocate, because if the allocate fails, I never had the memory in the first place, so there was nothing to have to catch there. So, where are the bugs? I've got a hand at the back.
Do you need to destroy in reverse order?
Should I be destroying in reverse order? That's my contract to choose. In about 5 slides' time, I do that, saying this is what people expect. We'll probably do that, but unless there's a relationship between the elements within the container that require that, which I would make part of my contract of my type, it's not necessary. But it is a user-friendly contract to do that. So I don't think that's a bug, but it's a good QOI issue.
Is this a constructor or what is it?
This is the constructor.
Why is it marked white?
Because it's a bug on the slide. Thank you. That's a bug I wasn't even aware of. Well done. Bonus credit. Anybody else spotting bugs on the slide? So I've got a hand here, and then you get to go.
Plus PTR?
Why would plus PTR be a bug?
Because we don't know the address difference between each element.
Bingo. Was that what we were going to say at the back? Or did you spot another one I'd missed?
Well, just wondering if initializer list should be a copy of the initializer list or by reference.
Initializer lists, we treat them as values, we always copy them. That's their intent. They're basically a couple of pointers internally. So
the allocator is by value. The allocator.
An allocator traditionally always passed by value. So the issue is, called out in red, that increment on the native pointer might not be the same as increment on the smart pointer. So these are the subtle things you have to think of when you start writing generic code, and be aware, keep your eyes open. So we end up actually with something that's a bit more like this. We make a copy of the auto putter because we're going to have one to reference if the in the catch clause maybe. But again, we can go through, we can construct passing address of star putter at each time we iterate through, and this should now largely work as advertised. Then we hit the quality of implementation issue that I'm now iterating through destroying these elements if the constructor throws in reverse order. So, sorry, I've got another slide here. People often suggest that, doing star putter and then a separate plus putter, sometimes it just might be more efficient this way. It's one less line of code. The star putter plus might be a little bit more efficient. It also gives me an off by 1 bug because I'll have incremented the putter before an exception is thrown. And dealing with that is much messier than simply actually just doing the right thing, which is separate the increment from the construct call. Subtle things just to be aware of and keep your wits about you as you're writing what looks like reasonably simple, straightforward code. So, final thing we do is we will then correct and unwind through the array in the reverse order of construction. So this is about, hopefully a worked example of what it's like to implement methods using the C++11 allocator traits. Does this feel reasonable, easy? People think they can follow this? About the end of those examples, very little code on the remaining examples. So now's a good time to ask a few questions. I've got probably about 3 minutes. Or we can just move on.
I have kind of an obscure question. You want an obscure question?
We'll take all comers.
So you mentioned that the reason that the construct extension point exists is that the allocator may want to do something unusual, like store cookies nearby the objects before they're constructed, or some other thing beyond just calling the constructor of the object.
So for the camera, I'm being asked, the nature of the construct customization point is so that the allocator might do something interesting as it constructs the elements, such as storing a cookie. So was there a question to follow up?
Yes. So when you called allocate, how was the space for that extra stuff taken into account?
So the question is, when I call allocate, if I've got a system that's storing this extra cookie at the point of that element, how is that taken into account? And that's the responsibility of the allocator, but it's probably going to be a consequence that it will allocate more space, managing alignment appropriately, and with a shared dance with the fancy pointer, know that that's how that's doing the offset with space interleave between the elements.
So that's why you pass in the number of things that you need space for, not how much space you need.
Correct. The question is that's why we pass a number of elements in the C++11 interface rather than a number of objects. So rather than a number of bytes. The amount of memory we don't know, it's whatever the allocator is going to return to manage that number of objects. So. Sorry. Jumping the wrong way through the slides. So got a last couple of corners of the 11 allocator model. First, we have another type trait, because we can never have too many traits. The user's allocator trait. This trait is fairly simple intent. It simply says, if I have an object of this type, does it use this allocator? So by default, the way we query this trait is, and you'll find this is true for all the standard containers, if your type has a nested type def called allocator type, we will see if allocator type is the same as T, or if I can at least use that in the family of T. And if that is the case, I know that you can use my allocator, and therefore allocator will return, uses allocator returns true. Otherwise, it returns false. But the intent is this is a customization point, because you might find something like standard pair. If I've got a pair storing strings, pair itself doesn't need an allocator. It's storing its elements directly in line. But it wants, in its constructor, to be able to pass the allocator to the strings that it's holding. So it can therefore customize the user's allocator trait by just generically forwarding to the allocator trait itself again for its elements and say, I use this allocator if my elements use this allocator. So therefore, if you're writing some code that says, if you use an allocator, I want to pass you an allocator, but if you don't, I won't. I can now sniff, can you use this allocator with the intent that it's following the allocator semantics? And if so, I can pass it to you. Otherwise, using those similar kind of tricks we saw earlier, I can go off and do the other thing. And the intent is, this is another popular place for the construct call to be doing this kind of work. Because the example I had earlier was the shared memory vector with a shared memory string. And I want to make sure the strings have the same allocator as the vector. So the vector is going to query the user's allocator trait and say, or the allocator that we were supplying in this case will query the user's allocator trait to say, can this new thing I'm constructing use the allocator? And if it can, I will add my allocator to the sequence of arguments I'm passing to your constructor. But we still need to know where to pass it. And unfortunately, I don't have a slide on that. And the assumption is, first of all, I will sniff out, do you have a first argument, a constructor that has a first argument, uses forgotten the name of the trait now. It's not uses allocator. This is uses allocator. Terrible. I should have put this on the slide. As a simple tag type, allocator argt or something similar to that says, yes, I'm going to do a construction using an allocator. My second argument will be the allocator, and then I forward all the other arguments. And the other idiom, because this is the way the existing standard was implemented, was the allocator's tradition with the last argument. So if I don't find this tag type as the first parameter, I will just pass the allocator as the final argument instead. And this logic is indeed all wrapped up in another class template in the standard library called scoped allocator adapter. This is the allocator you want to use if you've got the idiom that the elements in your container have the same allocator as the container itself. My classic example here will always be the shared memory allocator, because that really is a vital property for your shared memory allocators. So let's walk through an example of using it. I want to be able to write something simplish like I'll have a vector of strings using a memory mapped allocator for strings. So the memory for the vectors in shared memory, the strings are in that same shared memory, and we're all using these fancy pointers. Unfortunately, this doesn't work quite as written because I've said my vector is using a memory mapped allocator for strings, but the string I've supplied it is still using regular C++ allocators. So what does it look like if we try and do this in practice? Breaking this down to a few slides, basically it's the same slide, just going to highlight the text again. First of all, I'm going to open my own namespace at SHM. I'm going to create my shared memory allocator class, shared memory allocator. I have time for 15 minutes left. I think we should just come in good. And the first thing I'm going to do within my namespace is create an alias template, C++11 to the rescue again, called allocator, because that's a nice familiar term, so I can now use my namespace allocator. That is a scoped allocator adapter, that funky class template I was just talking about, that in turn will wrap a shared memory allocator. So now allocators in my namespace are actually scoped allocator adapters of my shared memory allocator. So the shared memory allocator I wrote the easy way, not having to worry about propagating allocators, because that bit's messy. That part has already been solved by the scoped allocator adapter. But I do need to have the composition as an easily available template, and that's what alias templates buy us. So I'm going to do all this in my namespace SHM, because that means I can then use very familiar names that people will expect to find from the standard. So I'm going to call my allocator allocator. I'm going to have an alias called vector in my namespace that's a straight alias template of standard vector, but by default we'll use my allocator instead. So you'll notice that the alias template in my namespace has one fewer template parameters, because I'm not giving you the chance to customize the allocator yourself. That's dictated by being in my namespace. But I'm not writing the vector code, because I can really hoist that straight out of the standard, and from C++11 it's going to work. Likewise, I'm going to have a vector of strings, so I'm going to have the basic string template. Everything in blue is the name from is coming from the standard namespace. That should have been really std char traits, but I was running out of width on the slide. And finally, we'll have the traditional using string equals basic string of char, so I've got the familiar string type def as well. Which means finally, where I want to create this, this vector of strings in shared memory, I just now use an SHM vector of SHM strings, and that has done all the wrapping of the scoped allocator adapters and done all the right things for me. And I can now initialize it using a traditional initializer list and have hello world. Almost. Because I've not yet said where to find the shared memory. A default constructed shared memory allocator is probably not what I want here. So after the initializer list, we're going to add a shared memory allocator. And I've not actually implemented the shared memory allocator. It's up to you to figure out what your interface is to construct and say how to find that shared memory segment. You'll pass that information to your constructor for the allocator. But at that point, we finally have our allocator with strings in shared memory. And final slide on this topic is, what did all that namespacing buy us? This is what our alias actually expands to if we were to try to spell it out. And I really don't want to tell my users to type all this in. Question? Why do I need the adapter? So the question is, why am I using this scoped allocator adapter in the first place? What scoped allocator adapter does is it uses the construct and destroy customization points I spoke about earlier. So in the construct method, it then goes to the user's allocator trait and says, is the element type I'm constructing, which I can deduce from the T star to the construct call, does that type use this allocator? And if it does, it will then pass that allocator argument as either the last argument as an additional argument to the constructor, or use the allocator arg t, comma, allocator if it goes at the front, depending on which of the two forms it sniffs out. But that's responsible for, therefore, propagating and making sure the containers are using the appropriate allocator internally. Any other questions? Yes?
So if you create one of these guys in the process, you're still going to have to use some sort of IPC to go to another process and find it.
So the question is, if I'm using this in my process and want to communicate it to another process, I'm still going to have to use some form of IPC to do the communication. And ultimately, yes. I'm creating my shared memory allocator, passing it information for where the shared memory segment is. I can read and write from that shared memory segment, but I still have no communication mechanism to say when to read and write and avoid races between the different processes. So I still need to manage that part of the communication myself. Any other questions?
When you were using it for the sequential stack allocator, what kind of performance difference did you get on your platform, the default?
I believe our recent benchmarks have been on the order of 3 to 5 times speed up. The standard new has got very fast over the years. It's been very highly tuned because people really want this to work. But we're still observing a significant enough gain for it to be worth us doing it. We additionally measured what happens if, rather than doing it through our dynamic dispatch, was the virtual function call overhead actually measurable in this case. Our general observation with our using polymorphic allocators on large systems is that in most cases the cost of allocation is such that the cost of a dynamic dispatch in the process is a wash. You don't really notice that cost there. But in this specific case, because you've distilled the behavior down to be that trivial and that simple, and you can even get more inlining because it's that trivial and that simple, we can probably get an order of magnitude if we even just lose the virtual function call and make it a really compile time type rather than a runtime type at that point.
It should be noted, too, that some portion, although we don't know that much also from Bloomberg, some portion of that speed up also comes from not calling the destructors of the objects you're throwing away. Because they're just on the stack and you didn't need to. So, but with the traditional allocation, you have a choice. They will be destructed.
I don't remember that being part of the measurement, because if the objects have non-trivial destructors, you have to run them. And if we have non-trivial destructors, we can normally optimize not having to iterate that loop anyway.
Maybe it's just the
allocation.
But we're not having to sub-allocate the...
allocation. Yeah, that's true. Yeah.
So the allocate is cheaper, but we still have to run the destructors if they're non-trivial.
Yeah.
Question at the front.
Have you compared your stack allocator with thread cache allocator from TCmalloc?
So have I compared our allocator, doing our stack allocation, with TCmalloc, I believe you said, from Google? No, I've not separately tested against other implementations. But
So I wanted to follow up on my question. So I create one of these guys in my process, and then I magically transfer some sort of pointer to the other process. Is there a way my allocator can essentially placement construct containers so that I have matching containers in both processes?
So the question is, having magically transferred my pointer from one process to the other, can I magically construct...
So I'm going to construct an allocator in my second process based on this pointer that I passed in, which will be in the same place in shared memory. And I now, using this new second allocator, construct my vector of strings here in place, basically, because it already exists from the first process.
So the question is, having got this pointer, how can I get or recreate the original vector that's already in the memory? And the intent is, if I have the shared memory allocator that knows about these process spaces, and the pointers come through in some kind of offset form, we should find that that memory, having essentially been allocated by that allocator, the data's just there. So there's a little bit about making sure that the pointers know how to navigate the process, and communicating the pointers might be a bit interesting. Typically, more likely, rather than pass the pointer value across, you'll say, here's the 7th element, but I can go and get begin plus 7, and I can now use that like an iterator in the other process. So I create the iterator in each process and find something to communicate to say how to find that iterator using methods that each process separately knows about.
Ownership of the object of the shared memory will be only by one process, the one which allocates and placed it on the shared memory.
No, I have a container that is using the shared memory allocator, and the lifetime of the object is controlled by whichever process wants to insert, remove, destroy those elements. And likewise, the management of the shared memory segment is managed by however you're managing your shared memory segment among your communicating processes.
So that's where the special pointers pay off, basically, because now it just works, and you don't care where you're coming from.
Yes, that's the reason why it's a fancy pointer, because the pointer is still working in offsets from the base of the shared memory segment. So wherever that maps to in the different processes, pointers within the data structure all have to be the fancy pointer type rather than native pointer types. That's why it's there. Yes, thank you. Good clarification. I have 5 minutes left.
I'm guessing that shared memory allocator has to be synchronized between processes, because if you're allocating using the same allocator to different processes.
So the question is, does the shared memory allocator have to be synchronized between the processes? Some form of synchronization is going to happen here. You might have various schemes that can allocate, but yes, it's your job to figure out how to solve some of these shared memory problems. I'm not solving the whole world for you. But for our experts in implementing shared memory systems, they can now plug this into a framework that will work with all of the standard containers. They no longer have to implement their own set of containers as well. And something I meant to mention at the start that always gives me problems when I first approach trying to learn about allocators, because what I should have mentioned at the start is most people, when they think about this, say, okay, I'm going to think of something simple to help myself understand the process. So I will assume I'm implementing a vector, because vectors are simple, which usually ends up with the end result that I would rather implement a special purpose vector than do all this craziness with allocators, because I can do a vector simply. Whereas if I think of this as, say, an unordered map, I would much rather go through the allocator craziness here because it comes out to something fairly simple to use than actually trying to implement a shared memory interprocess unordered map. So if your mental model is vector, you're not going to get the best of trying to understand the benefits of why building this into the allocator system rather than each container is a way that makes progress. Unfortunately, it's 2 hours late to be making that point. Question at the back.
Speaking of not solving every problem in the world, one problem that I've always had conceptually with allocators is the rebind allocator part of it, where I have an allocator of T, and it needs a method, rebind, that will create an allocator of U. If I'm doing a pool, where I have a pool of 8-byte doubles, and suddenly it says, I need an allocator of node of double that's 23 bytes, and suddenly I have to figure out, how do I get a 23-byte object out of my pool of 8-byte objects? Do you have guidance on what it means to rebind an allocator?
So the question is that the rebind interface is often doesn't solve all the problems of the world. So the rebind interface we have is very handy for when I've got allocators of the same type interoperating on different element types they create, because the rebind will tell me the type of the allocator I want, and all the allocators will be able to construct from any other allocator of the same family from that same template. There's an implicit conversion constructor. So I can just create an allocator that will allocate the things I want to allocate, pass myself as a copy, so it's now coming from the same external resource, because remember I said that our resources are going to be outside the allocator itself. This is an interface of how to manage that external resource. So I can now just create an allocator using the rebind from the traits to say, give me an allocator of the right type to make those kinds of things, and just use it.
I'm not sure I follow.
I can probably can't quite interactively jump back enough slides because we're back about 7 dozen or something. It's worth trying anyway. Go to it. Yeah, here's our simplest allocator. So the idea is the white constructor at the top says any constructor, any allocator that comes from the same template family can make one of these. So I use the rebind from the traits to say, what kind of thing am I allocating? Give me an allocator for that kind of thing. So in your case, a pool using something of size 23. And I therefore say, okay, and now I've got that kind of constructor. I can pass myself saying, okay, whatever I say about making objects of pool 8, this is where they're coming from. It's my job with that converting constructor to say, now I know how to turn that into something that can pool and make something of size 23. So it moves a problem to this constructor maybe, but it shouldn't be a problem for the clients. Could be a problem for the allocator implementer.
The allocator implementer is the guy implementing that constructor, isn't he?
Yeah. But I mean, you know what the interface for the pools that you're managing. So if you don't know how to interoperate your pools, you're not in a position to be writing these constructors in this allocator yet anyway. If these pools are intended to interoperate, I'm going to be holding a pointer to this is where my pools are, this is what the pool resources look like, and therefore my allocator, having constructed the next pointer, says I know how to use these pools in this way for my other types. But it's my job to know how to write that part of the allocator. It might not have, that might not be solving the problem for you, but that's where it drops into the system.
But that constructor is required, though, right?
And this constructor is required as part of the contract of being an allocator, yes. Question at the back.
Yeah, is it the case for allocator implementers that we should be thinking of pools in terms of pools of raw bytes rather than pools of fixed size objects? Then the rebinding problem goes away because you're interpreting a pool of bytes as double or a pool of bytes as string.
So the question is, if we're thinking in terms as allocator implementer, should we be thinking purely in terms of pools of bytes rather than pools of sequences of certain size? Yeah. But I don't think that's very helpful because the benefit of the pool comes from being able to manage objects of specific sizes. That's one of the optimizations we're trying to achieve. But we still need to know how to manage objects of different sizes within the allocator rather than within the container. It's the allocator that solves that problem in one place, and then all the containers that want to allocate things of different sizes can all work with that family of allocators. Time's running up. In fact, time is over. So I'm running completely the wrong way through this. My last 5 slides are a very quick sequence of bullets. But there's no quick jump 10 slides or something. Yeah, a couple of rhetorical questions. So, who needs to know how to write allocator traits? I do. And I'm possibly the only person in the room that needs to know that. But your standard library vendors need this. It's fun to know. It's fantastic exercise if you enjoy playing with templates, and it's purgatory otherwise. But this is very specialized knowledge. Who needs to know how to use allocator traits? Slide's running away from me. Anybody who implements a container or something that's going to manage resources. Who needs to know how to write an allocator? People who have something very specific they can do in terms of implementing allocators. They're solving very specific problems. It's handy for the container authors to know this, but these could be quite distinct groups of people. But as a container user, you want to have an idea of what the allocator folks might come up with, even though you know it's coming through the traits interface. Who needs to know how to use an allocator? I'm going to argue pretty much everyone else. They're very useful things when you have them available. And that is my last slide. Thank you.